Hi everyone, just doing another video, this time on a question. It's actually question 7 from step 2, 2014. Partly doing these ones just because I noticed that I hadn't got all of 2014 done in my notes when I looked in my folders, so I thought I'd better get the last half of the pure ones done here. And secondly, I've done recently 2 or 3 modulus questions, which I think are some of the nicest ones you can find on the step once you're aware of things like how to sketch these graphs, critical values, like what's a sensible way to approach them. They're really not that bad then, and also it's good for your understanding of modulus functions in maths and further maths. So they're quite nice ones to do when you first start doing things like step. Granted, they're not going to necessarily be mega useful for math. Although that said, I think in 2023 or 2022, sorry, last year's most recent MAT, the very first question was basically sketch a modulus function. Why? Or if you sketched the modulus function, you would have done it way quicker than if you tried to solve it. So, these are popping up in these extension papers, so let's have a look at it. Now, the first question, y equals x minus a in a mod plus x minus b in a mod. There's a really standard way we can sketch these kind of things. There really is. And maybe I'll just quickly explain, as I have done on another video, how I might sketch something like this. If I was sketching something like that, because it will be way more obvious if I do it with numbers first rather than letters, then you'll see exactly where I'm coming from. Okay, if I was going to sketch something like this, there are what we might call critical values here. Those critical values being -1 and 3. The critical values being the values which make the expression inside the modulus 0. Because obviously when you're less than -1 here for x, this is going to be negative and the modulus is going to behave in one way. But when you're more than -1 here with x, x plus 1 is going to give you a positive value, and hence the modulus is going to do nothing at all. And so if you look at those critical values, that is the way to sketch this. So I normally do it in a table, and I call it like CVs, just for critical values. And I just point out, well, when x is like, let's say, less than -1, and then if x is between -1 and 3, and when x is greater than 3, this expression is going to behave in 3 different ways, basically. Now, what's going to happen when x is less than -1? And we're trying to think what y equals here. I'm trying to write what y equals here. Well, when x is less than -1, this is actually going to be a negative, this bit, yeah? And therefore, we're actually going to get something which we're going to have to change the sign on. So you're better off looking at this as not x plus 1, but rather -x minus 1. Yeah, in other words, you just change the sign of it because you're going to times that by -1 when x is less than -1, yeah? And likewise over here, if x was less than -1 here, if you had -1, -3, you got -4, and if you had it less than -1 here, you're going to get a negative here. So if we change the sign on both of those terms, you'll realise that that is actually the same as what is that? -1 add 3 is 2, and then take away 2x, yeah? So in other words, this expression is exactly the same as y equals 2 minus 2x when x is less than -1. So it's going to be, if you like, on a graph, coming down, like what does graph of 2 minus 2x look like? Well, it's obviously got a negative gradient, and it hits the y-axis at 2, but we're only interested in it when it's less than -1. Now, what about when x is trapped between -1 and 3? Well, at that point, this one is going to be positive, but this one is still going to be negative, and therefore this one's still going to be an x plus 1. We don't need to change the sign on that, but this one is going to be a 3 minus x, and so you're just going to end up with y equals 4 when x is stuck between -1 and 3. And actually check it. Let's see if x is 0. Do we get 4? We get 1 plus the mod of -3, which is 1 plus 3, which is 4. Do you see what I mean? Like, and that was just picking x is 0. If I pick x is 1, I'm going to get 2 here, and I'm going to get, if x is 1, I get 2 there, and then I get 1 minus 3, which is -2, make it positive 2. 2 plus 2, 4. Do you see what I mean? Y is always equal to 4 when x is stuck between those values. Now, when x is bigger than 3, well, that's the case where the modulus isn't going to do anything to either of these expressions because they're both going to be positive, and so you're going to have x plus 1 plus x minus 3, and therefore you're actually going to have y equals 2x minus 2. You're going to have the negative of that one. And that's why this is actually going to look like this. It's going to go down, it's going to be flat, and then it's going to be going up, and the gradient there is going to be -2, and the gradient here is going to be 2. But that is the most sensible way of sketching mod graphs when you've got a series of like linear mod expressions. It comes up all the time on these extension papers, and if you know how to deal with it, it's really not that bad. So okay, let's go back to our original question. What's it going to look like? Well, we've got it just generalised with A and B, but A is the smaller one, so we can do a little CV table. We can say x is less than A, x is stuck between A and B, and x is bigger than B. We can do exactly the same process of finding out what f of x equals for these particular situations, and f of x is going to equal, well, here they're both going to change sign, because if x was less than a and a is less than b, that's going to be negative and that's going to be negative, so you're going to have a minus x plus b minus x, and that is of course a plus b minus 2x. That's what you're going to get for your f of x here. Let me write it down with the f of x equals so it's a bit clearer to you. So here you're going to get f of x equals a plus b minus 2x. In the middle you're going to have, well, as long as you're bigger than a, this is actually going to be positive, but that one's still going to be negative, and so you're going to have x minus a plus b minus x. The x's will cancel and you'll just be left with f of x is b minus a. And here neither of them actually change sign, and so you've got x minus a plus x minus b. And so you've got f of x equals 2x minus a plus b in brackets, if you like. It's the negative of that one. And so when we're sketching it, it's going to look really like this, but without the -1 and 3. It's just going to have the a's and b's in it. And here's another lesson for, you know, how to be successful on these papers. When they introduce constants, use numbers if you're happier using numbers, and you can just be sure that it's going to work the same way with the constants, really, but you just be left with the constants in there. And so my answer to the diagram, at least for the first one, is something like this. Let's try and make that a bit neater. Try and show the gradient, or at least keep it in mind. They actually told you to write down the gradient at each point. That's a gradient of 2, that's a gradient of -2. This is obviously a gradient of 0, and it is going through b minus a there, and this is a, which must be less than b. Yeah. Now that gap is b minus a, and this height is b minus a, so this actually should be a square, which is part of the question. Have we done? Yeah. Oh yeah. I've just got to sketch g of x on here, but I just like to point out that a0, b0, bf of b, af of a, that's in fact this shape here, and it doesn't look like it on my graph, sure, but that is actually a square. Is a square, yeah. And last thing they wanted me to do here was they wanted me to draw g of x, which is the mod of 2x minus a plus b. Yeah, this is their g of x. Why has it gone funny colour? Oh, maybe I'll try this. G of x, which is a mod of 2x minus, and I'm just going to put it in brackets a plus b, because then it makes it more obvious that this is exactly the same as this, and you've either got 2x minus a plus b whilst x is greater than a plus b over 2, which is this point here, or you've got the negative of that, which is coming down there. And so if you like, this is like you know, it's exactly the same as the graph above it, apart from in the interval a to b, where you end up with like the shadow of it. I would denote it like that on my graph and put the thick line as f of x. I'm having trouble with colours at the moment. Yeah, and hopefully they can see what I mean there. I will probably explain it a little bit further as well. I like getting full marks, obviously. Sometimes when I'm doing these videos, I don't necessarily write it down exactly like this in the test. It's slightly difficult actually working on a graphics tablet. It really is. It's a lot easier on paper. So I hope that first part of the question makes sense. Yeah, it's a nice question, and it doesn't get that much worse. It really doesn't here. So let's just pull this down so we can still see it, what we're doing. show graphically that this equation has 0, 1 or 2 solutions, stating the relationship of c to a and b in each case. Okay, right. We already know what this looks like. Yeah. Let's draw it the same way as before. It's got a gradient of -2, then it goes flat, then it's got a gradient of 2. Yeah. Remember that gradient of 2. Now let's draw this now on the same graph. Well, that's a really easy one to draw, isn't it? It's simply got its pointy bit, if you like, at C. Yeah, let's put C here first. But it's going to have a gradient of 1, not 2, so it's not as steep as that. And you always want to show that when you think about other modulus graphs you've done before. Always show the steepness. It's a really crucial thing to do. It really is. Now, clearly, the way I've drawn it here, with A there and B there, if C is in between A and B, because the gradients are 1 and -1, whereas these gradients are 2 and -2, and this is a square, remember? Yeah, this is a square. It's only going to be when C is at B that that's going to have a gradient of -1, and it's only going to be when C is at A that from here to here you're going to have a gradient of 1. And that's just because the diagonals of a square have a gradient of 1 or -1. And so we can see straight away after sketching this, like immediately what the answers are. Yeah, you can say whilst A is less than C, which is less than B, it will have no solutions. Yeah, there we go. We've stated the relationship of C to A and B and said it will have no solutions there, because you can just see it's not going to touch. But when C equals A or C equals B, it will have one solution. The reason being, and if I can just quickly change this, I would probably draw a separate diagram actually for each one. Yeah, so let me just put that attached to that diagram. It just makes it really obvious to the examiner. You know, I've just looked at today, somebody sent me their paper to have a look at, and it always amazes me, never ceases to surprise me, how strict they can be on some questions about taking marks off when you've absolutely done what they've asked. So, you know, be paranoid. Now we'll just draw that same kind of shape again, that kind of almost bucket shape. Remember, it's a square, and so if you've got a situation like that or like that, in other words, when C equals A or B, yeah, you can just say when C equals A or B, it will have two solutions. Sorry, it will have one solution. Now, how do you get two solutions? Well, guess what? It's when C is less than A or when C is greater than B. And that's because it's going to hit twice. If we move this one a bit to the left, it's going to hit there and there. Yeah, so you can just draw that now. Make it nice and clear to the examiner. Bucket shape again. And now let's have it over here. You know, yeah, the gradient isn't as steep, but it could do something like that, yeah. Or you could have something over here. Same thing, yeah. Call them C1 and C2. Yeah, just point out when C is less than A or when C is greater than B, it will have two solutions. There we go. I love these modulus questions, I really do. They're some of the ones which I feel most confident on when I'm doing these kind of extension papers. And it's good to have a few topics, isn't it, where you like actually feel pretty confident on that. Some of the mechanics questions, honestly, and I'm, as someone who grew up like, you know, with a severe phobia of mechanics, I love them now, I really do. And so they can't be too bad, really. They're really pure maths in disguise. Same with the stats. Stats is the same. I'm not doing as much stats in my teaching recently, and so I don't feel quite as confident doing them, but I used to love them. So yeah, worth having a look at if you're doing STEP. Honestly, don't dismiss them. Don't dismiss them. Some of them are actually really quite nice. Okay, so this equation, well, it looks like we're dealing with basically two bucket graphs, if you like. I think they're kind of in the shape of a bucket. Let's just draw our first bucket. Try and make it look squarey. But what we do know is that d minus c is smaller than b minus a, and b minus a is the length of your square. So if you like, it's like it's going to be a smaller, more it's just going to be of smaller orientation, but it's still going to have gradients of 2 and minus 2 there and there, and that's very important, yeah, because if you're thinking about what could possibly happen then, well, there's really not that many things which could happen. We could either have this situation. Let's draw one where, I don't know, something like this, yeah? We could have something like that. It's supposed to look like a square at the bottom, so we could have a D and a C here. Oh, hopefully that's not clear enough. Yeah, could be there, it could be on the other side. Now I'm just going to lengthen it out. Now one thing I do know about that line and this line is they should be parallel. They should have exactly the same gradient. So let's try and make it look like that. So that's definitely not going to intersect that bit later. It's not steeper, it's not as steep, it's parallel. And this line is parallel with this line. So this is just going to shoot off there like that and stay parallel to that line, and this one's just going to stay parallel to that line. Yeah, well, you can see here that you're always going to have one solution as a result of that, at least one solution. Yeah, whatever happens, there's always going to be at least one solution. So I might write down first initially, clearly there's always at least one solution. There's always one line which is going to be parallel to the other one and not hit, and there's always the other line which is going to which is going to hit either the diagonal bit or the flat bit. Yeah, there's always at least one solution. Now, how can we get more than one solution? Well, the only way we're going to get it is if we actually overlap one of the parallel lines. Now, when does that happen? Yeah, well, let's just use our imagination a little bit. It's going to be when we have a bucket like this and maybe something like that, and that's supposed to be going over that. Maybe I should have done that in a different colour. Let's do it in red, this bottom one, just so I can kind of show you. It's going to go over the top, yeah? Okay, now when is this going to happen? That's the big question. Well, here's your A, here's your B, yeah? Remember that this is going to be the case, well, for both lines, you both get like y equals 2x minus a plus b for the first one. And so you need that to be the same line as the second one, which is 2x minus c plus d. Yeah, in other words, when a plus b equals c plus d. And it's just occurred to me that that actually isn't possible unless this one is also overlapping this one, so I haven't drawn it correctly, because it is going to definitely overlap both. When that's the case, you're going to have, done a terrible job drawing it there, but let me do it in red. And it's really the algebra which has just convinced me of that, because it must be the same on that side as well. So yeah, there's your I think D was bigger than C, wasn't it? Yeah. And so there you go. That's what you're going to get. And you're also going to get that lovely fact about a midpoint, which is why I guess they got you to draw g of x at the start, because b plus a over 2 and d plus c over 2 are going to be the same then as well. And so then you'll get infinite solutions. Now, do ponder it and think, is there any other ways we could get those intersecting, or like, not intersecting in any way? And I hope after a while, because you've got one which is just a scale factor reduction of the other, or one's a scale factor enlargement of the other, I hope you can quickly convince yourself there's either going to be one solution or there's going to be infinitely many. So either a plus b equals c plus d, and there will be infinitely many solutions. There will be an infinite solution set. I can't remember if it actually asked us for the solution set. No, just the number of solutions stating the relationship between A and B and C and D. Or a plus b, doesn't equal C plus D, and there is just one solution. So there we go. I thought that was really quite a nice question to demonstrate. It's one of these nice friendly modulus ones. We'll do tough ones next time, because you're probably thinking, yeah, well, that's the odd modulus one which I might get right. What about the others? And I agree, these ones tend to be friendly. I mean, this is a step 2 question, like they tend to be fierce, whereas that you can do with just a few pictures pretty quickly. So the exception rather than the rule in terms of step levels of difficulty. But I hope you found the video useful, and keep up the practice. Bye bye.